All right, so we are going to start 10.8, and I want to look at the arc length of these space curves. So we're talking about vector functions, functions that look like this, and we're going to limit ourselves to vector functions that trace out their space curve exactly once as t goes from a to b. Let me show you what I mean. Suppose that my space curve never closes. Well, then that's not a problem. We have to pick a ending point. Oops, I kind of went off the screen. We have to pick a beginning point and an ending point, right? And so that's where the a and the b comes from. Otherwise, you'll have infinite arc length. Second thing is, what if your curve is closed? We don't want to go around it and around it again and again and again. When we're talking about length, we're assuming the length of the curve traversed one time. So that's what we're talking about here. And we're going to restrict to functions with bounds on t that only go around the curve one time. Okay, in that case, the arc length of the space curve given by r of t is, well, it's L equals the integral from a to b of the length of r prime of t dt. That's it. But please realize this is a scalar. And so this whole integral is a Calc 1 level integral, at least in theory. And so let's go ahead and write another version of it. So integral a to b, we can actually compute what is the length of r prime. Well, it's the radical of f prime of t squared plus g prime of t squared plus h prime of t squared. I need to extend my radical dt. All right, so you've seen this before back in Calc 2 when you guys talked about parameterizations a little bit. And it's the same sort of formula. I'm not going to take a lot of time to justify it. We could spend some time trying to understand where it comes from, but I think in this section we're going to just dive in and do some examples. Got some mixed colors going on here, sorry. So I want to find the arc length of this guy over this interval. And by the way, once you saw the examples in the last section, you should recognize this is a spiral stretching along the y-axis. So I've got x is cosine, y is sine, that's a circle, and this is in the xz plane, and then we're going to stretch it out along the y-axis, something like that, if it helps. You don't have to be able to visualize it, but it's sort of somehow nice to be able to do that. So I want to find the arc length of this curve from 0 to 2 pi, and so I know right away that the arc length L, is the integral from 0 to 4 pi, I'm sorry, not 2 pi, integral from 0 to 4 pi of the length, I'm just going to write it down, length of r prime of t dt, and this is the integral from 0 to 4 pi of, the square root of, all right, so derivative of cosine is minus sine, square it, and you get a sine squared t. Derivative of t halves is 1/2, square it, you get a fourth, and then the derivative of sine is cosine, square it, you get a cosine squared t dt, and that's it. And maybe this seemed intimidating when you first saw the formula, but in this problem, sine squared plus cosine squared is just 1, and so I end up with the integral from 0 to 4 pi of the square root of 5/4, that's all under the square root dt. Well, this is just root 5 over 2 integral 0 to 4 pi dt. Somehow this is a letdown. It wasn't that bad, right? And so I just end up with 4 pi times this constant. The 2's cancel, so I get 2 pi times root 5, and that's my arc length. Okay, I'll end this video here with a little comment. I'll slide it up actually. The arc length formula is independent of the parameterization that you choose. You may remember back in Calc 2 when you were learning how to parameterize things that there's different parameterizations for the same curve. So if I wanted to trace out this spiral that we're talking about, this formula restricted to 0 to 4 pi is one way to do it, but there's actually other ways to do it as well. And it doesn't matter which one you pick, the arc length is going to be the same. So you don't have to stress about are you changing anything or not. All right, well, let's break this video here, and in the next one we will talk about the arc length function.